All right, welcome back from our short break. We will now be continuing the 2018 Cuba Infrastructure Scholarship Competition. Right before the break, we had the University of Alabama present on dual mode transit. Up next, we will have the University of Florida, Team Chomp Wastewater. They will be presenting on the design of microalgae-based wastewater treatment plant for the Havana, Cuba, for use in Havana, Cuba. We are excited to have the students from the University of Florida join us today. Juan Jane, Mayu Mizutani, and Chang Peng, who may not be here today. Their faculty advisor is Dr. Ben Koopman, and their industry advisor is Eric Antman. So please welcome this team of two young ladies up to the stage.
And thank you, Regina, for the introduction. My name is Juan Jane. My major is environmental engineering. I'm current a PhD student.
Hi, thank you so much for having us today. My name is Mayu Mizutani. I'm a third-year undergraduate student at the University of Florida studying environmental engineering sciences. To begin, we will be introducing our topic with some background information and some context for the purposes of our presentation, and then moving on to our method of designing the wastewater treatment plant, our feasibility, including land use and population statistics, and a cost and benefit analysis. To begin, I'll be describing briefly about the characteristics of wastewater. Typically, there's BOD, or biochemical oxygen demand, and COD, which is chemical oxygen demand, which typically describes the or oxygen depleting species in the wastewater. And this is especially important because with too much BOD or COD in the wastewater, it will make the receiving waters, such as the surface waters in Cuba, to be anaerobic, which will suffocate organisms and flora in the wastewater, the receiving waters. So we will be treating this wastewater to remove the pollutants from the wastewater, to promote public health, to preserve aquatic life and wildlife habitat, and to promote recreation and quality of life in Havana, Cuba. There are some conventional steps to treating this wastewater. Typically, we start with preliminary treatment, which usually includes grit chambers or a large filter to remove the large floating debris. This typically removes 100% of large debris. Then we move on to primary treatment, which removes 60% of solids and 35% of BOD. And usually this consists of a mechanical process, including sedimentation tanks and separation by flotation. And secondary treatment removes 85% of BOD, and this is usually consists of biological treatment, such as activated sludge processes. And then finally, we would do tertiary treatment, which includes chlorination and filtration by use of biochar, activated carbon, sand, and anthracite, which removes 95% of the remaining BOD and solids, as well as nitrogen and phosphorus. For the purposes of our presentation, we will be focusing on primary and secondary treatment. So in Cuba, the wastewater treatment crisis is occurring in much of the surface water, and the surface water accounts for 65% of the Cuba's available water supply, and there are 8 priority watersheds, which serves 40% of the population. As you can see here, there are existing wastewater treatment plants in the lower Almendares River, which is the Maria del Carmen wastewater treatment plant. and then above the Havana Harbor, which is the Lower Luyano and Upper Luyano wastewater treatment sites. However, unfortunately, these are not operating up to capacity, which means that a lot of the wastewater discharge from industry, agriculture, and municipal wastewater is discharging directly into the surface waters. And you may know that the Almendares is hydraulically linked to the Vento Aquifer, which is a lot of the drinking water supplies in Cuba. Havana. So currently, the demand for wastewater treatment is to serve 2.2 million people in the entire country of Cuba, and the overall demand is 0.6 million cubic meters per day, or 0.27 cubic meters per person per day. However, the capacity is that only 2 large plants are operating in the entirety of Cuba, and they're only at 30% capacity, which means that even if all of the capacity of wastewater treatment plants were in operation, they would only serve about 15% of existing wastewater effluents. So clearly the current wastewater infrastructure is not sufficient to meet the demands of Cuba, especially Havana City. So we plan to solve this wastewater issue using a microalgae-based wastewater plant. This microalgae-based wastewater plant utilizes microalgae, which is microscopic photosynthetic algae, which characteristically has a rapid growth rate, as well as the highest biomass production per surface area than any other organism. And because they produce biomass using photosynthesis, they can incorporate important nutrients such as inorganic phosphorus and nitrogen into their biomass to reduce the amount of nutrients in the effluent of the wastewater, which would cause eutrophication in the receiving waters. And because they can incorporate inorganic nitrogen, phosphorus, and even heavy metals, this can be used to treat industrial, agricultural, and municipal wastewaters. And we chose microalgae-based wastewater treatment plant because we believe that the conventional wastewater treatment plant was not sufficient to meet the needs of Havana. Conventional wastewater treatment, including activated sludge processes, requires a significant amount of chemical additives and energy to aerate the wastewater, while microalgae-based wastewater utilizes solar energy as a main driving force for the mechanisms in the wastewater treatment. So the input of solar energy reduces the need for mechanical energy or chemical energy. And conventional wastewater treatment creates a secondary sludge which is hard to manage and dispose of, while microalgae-based wastewater treatment creates biomass which can be used to create biofuel or biogas to either sell it to the public or to feed directly back into the wastewater treatment plant. It was successful in the past, not specifically for microalgae, but a biomass-based wastewater treatment plant was successful in Cuba at a pilot plant utilizing hyacinth, which is a water plant, and it incorporated BOD, TKN, which is total nitrogen, total phosphorus, and total suspended solids into their biomass, reducing eutrophication in receiving waters. And there are successful examples of integrated microalgae ponds and high-rate algal ponds in New Zealand and rural California. So our goal is to design a microalgae-based wastewater treatment plant for a total of 10,500 people to produce 2,835 meter cubed of wastewater per day, utilizing its low-cost, high-efficient, and low-energy need wastewater treatment plant. And this is modified from our original proposal, just scaled down by a factor, just for ease of presentation.
So here is our overall design of the wastewater treatment plant. It may contain 4 processes. The first one is a preliminary treatment, and we just talk about the preliminary treatment process. We will use the filters to remove the large solids, and the second one is primary treatment. We will use the covered anaerobic plant to digest the pollutants in the wastewater using the anaerobic digestion. And the third one, we will use the high-rate algal plant as a secondary treatment process to further digest the organics and inorganics in the wastewater. And the final is we will use the algal harvest method to collect the biomass and resupply to the covered anaerobic plant. So the first one is a preliminary treatment. We will use the bar space at 20 to 60 millimeters at a flow rate range of 0.2 to 0.4 meter per second to remove the large solids. And the remove efficiency of large solids can reach to 100%. And the next one is primary treatment process. We will use a covered anaerobic plant. We call it CAP. And the objective is to remove the most organics and inorganics in the wastewater. And this principle is to use the microalgae to digest the pollutants and under the anaerobic digestion process. And the energy output is methane, so the methane can further be used to generate the electricity. So it is very energy efficient. And the efficiency to remove the pollutants is high. It's about 60 to 90% of BOD and 50 to 7% of the total suspended solids, and even the 60% for the oil and grease. Here's a diagram of our design. Because we want to extract the biogas from the CAP plant, so we will cover the CAP using a specific material. And we want to meet the capacity of 2,800 cubic wastewater. So we plan to build 2 CAP plants, and then the CAP plant will require 20 days retention time. So based on our calculation, the plant volume of each should be about 28,000 cubic. And the guideline of the CAP construction require that the plant depth should be less than 6 meters. So we use 6 meters for the plant depth, and the freeboard height, it is here, the freeboard height should be less than 0.6 meters, and we use 0.5 meters for the freeboard height. And based on these parameters, we calculate the land use of the CAP plant is about 6,000 square meters. And here is the secondary treatment process. We will use a high-rate algal plant. This plant is open plant, so it uses solar energy to convert the biomass, to convert the pollutants to biomass. And to meet the capacity of 2,800 cubic wastewater capacity, we calculate the size of the HRAP, and it requires about 12 acres. And
so at this point in the wastewater treatment process, there is a lot of total suspended solids, including the microalgae biomass in the wastewater. So after the high-rate algal pond, the wastewater would flow into the microalgae harvest and clarification settler, which is a lamella plate separation clarifier. Because microalgae has a small size and small mass, the settling velocity by graveling alone is very, very slow. Therefore, it's very inefficient and difficult to collect the microalgae and clarify the wastewater effluent just by gravity alone. In addition, separation by flotation is expensive because of the increased need for aeration, and we utilize the microalgae method to get away with the flotation completely. And coagulants such as alum and ferric chloride disrupt anaerobic digestion by creating a film around the agglomerate of microalgae, so that was not an option for us. So we looked at a case study in New Zealand that utilized lamella plate separation. So the water would come in through this inlet, and it has suspended algae and total suspended solids within. And it would flow in, and then the flow rate would temporarily stop, and then have gravity settle the suspended algae and solids down and slide down these lamella plates, and then this sludge will accumulate at the bottom, which will be pumped back into the covered anaerobic pond for anaerobic digestion. And then the clarified effluent would be flowed out through this outlet here. And this method would increase the settling velocity by a factor of 490 times. So we would have two clarifiers for this presentation, and then the number of inclined plates per clarifier is 7, and at an angle of 50 degrees to reduce clogging, and then also reduce the need for backwash, which requires a lot of energy as well. And then the total suspended solid removal efficiency is 90%.
So make sure the waste plant work the best. We need to check the conditions of the wastewater treatment plant because the algae, they require specific environment to grow, and the main factors to affect the microalgae growth, including the light and temperature. And because high rate algal pond, it is open pond, so the light and temperature will depend on the ambient conditions. And we look into the climate conditions in Havana City. It is pretty good. The average temperature ranges from 21 degrees C to 27 degrees C. And even though in summertime it has rainy days, but the sunshine hours still can reach to about 10 or 11 hours. So it is feasible to build a microalgae-based wastewater treatment plant in Havana. And also, the land use of our treatment plant is not large, and we look into the topography in Havana City. The elevation level is not high in Havana, so it is also feasible in terms of the land use. And we also calculate the cost and benefit. The total investment cost, including the construction and also the materials, will be about 2 million and 1 million, and the yearly operation and maintenance will be around 10,000. And we also calculate the benefit. Including the heat revenue and also the utility revenue from the local residents, and also the fertilizers that coming from the biomass generated from this treatment plant, and the total revenue could reach to 0.6 million per year.
To conclude, our proposed microalgae wastewater treatment plan is to treat 2,825 cubic meters per day with a population of 10,500 people. Our annual benefit is $672,000, and we believe that Havana has a sufficient topography, land use, and existing infrastructure to provide an efficient solution to untreated municipal, industrial, and agricultural wastewater treatment or wastewater in Havana, Cuba. Okay.
We want to thank our advisors, Rachel Liu, Dr. Ben Koopman, and Eric Antman, and we also want to thank Dr. Yu Hu for providing a lot of suggestions on our project. And thank you. Any questions?